Now we have seen that matrix form is an efficient way to present the solution or the estimates from OMS estimator. I hope you feel already motivated. We will go now in the next 4 slides in details how to set up the GLM models in matrix form, how it works with the estimator and the assumptions, and so. So these 4 slides actually very important, not only for this week, but also for the lectures in upcoming weeks, so please pay attention. Whenever necessary, I will stop to explain to you and also illustrate directly with the further example the rule of matrix operation. So let's go first with the notation of the GLM and the setup. Let's tie directly to our burger chain example, but now I replace the TR with the Y as the general notation for dependent variables, so that it's more consistent with the textbook and confuse you less. And here I assume we only have 4 observations in the data set, so it's simpler. And this is what we have known already before. For each observation, we have an equation for yi, or the total receipt, explained by one intercept, the coefficient times the, what's that? Price, right, average price, and then another coefficient times the advertisement expense. So this is for each observation in your data set, and when you summarize it by matrix form, it will look like this. So up to this point, there are at least 2 questions you can ask yourself. First of all, why x times beta, but not beta times x? What's the difference, and whether we can reverse the order? The second thing is why here we start with xi2, but not xi1. Where is it? So we will answer this question later, but let's look at the vectors and the matrix in this form first. So the first one is y, the vector of dependent variables. Vector because we only have 1 dependent variable for now, right? So you call it the vector when it only has either one row or 1 column. So in this case, you have all the observation of dependent variables stacked in 1 column. So it's called column vector. Or in some software you will see also the word array. So when you talk about matrix or vector, it's important to talk about the dimension. Sometimes it's also called the order. So the dimension tells you how many rows and how many columns the matrix or the vector has. So by construction, vector only has either 1 row or 1 column. In this case, we have the column vector, so it will have only 1 column, right? And because we have 4 observations, 4 elements, so the number of rows is 4 times 1 column. One mantra to remember right now is when we talk about the dimension of matrix or vector, rows come first. The number of rows times the number of columns. This is important, keep that in mind. And each of these E1, E2, E3, E4, we call it element. Okay, so Y has dimension 4 times 1. If you have n observation, then n times 1. Let's move on to the matrix X. Let's look at the dimension first. Well, you may wonder already why there's a column just with number 1 everywhere here. Go back to that later. But for now, let's count simply the number of rows. 1, 2, 3, 4, because 4 observation. 4 times 1, 2, 3. Okay, so that's the dimension of matrix X. Now, if you imagine seeing a data set in Excel or other statistical software, you also see it the same thing, right? Observation, 1 below the others, and then each column for 1 variable. So let's try to tie it to our mind a bit. And then the second thing, why there is the column 1 and why there's 3 columns where we have only 2 explanatory variables. Well, short answer right now is the first column is for the intercept. You need a column of 1 so that later when you multiply it with beta, you will have this beta 1 in your equations. If you don't have it, you can't. But we see it when we come to the multiplication of matrix, okay? So now beta, because in our example we have 1 intercept and 2 other coefficients, so at the end the beta has 3 elements, right? So a column vector of 3 times 1. And then the error term, last but not least, they're actually very important. But the dimension of the error, because we have 4 observations, so now we have 4 times 1. This is the dimension. So you can see the column vector is actually a matrix with only 1 column. No? So if you have a row column, if you have a row vector, that means a matrix with only 1 row, right? Now let me go back to X here, a few things to add. Pay attention. In general, now when talk about, for example, OLS or GLM, the dimension of the X matrix is n times k. Now, so because we add this column for the intercept, keep in mind that k includes already the intercept. Now, for example, when you read the physics textbook, usually with some calculation involving k, that you understand that the intercept also counted inside. Now, the second thing, just like the way we have the mantra with the dimension, when we talk about a specific element of the matrix, we also refer to the row number first and the column numbers later. So for example, x12 means x on the first row and the second element, right? So that is for the setup, and this terminology you can find on your slide 40. No? So because I want to really spend more time on the next course slide and tie the matrix operation application to those slides, I would not have time for the slide from 13 to 25. You would have to go through it yourself for other general rules. However, I will also upload the videos of Professor Heckelai that he did for last year, in case you want to watch. Okay, now we're done with the setup. One more thing. So imagine you have an array A in which there's only one single element, A1. Then A is called a scalar. Yeah? So a matrix or a vector with only one element, which is actually what we're dealing with, or what we have to do with all the time, back to the time we did microeconomics. Yeah? Then the next thing is we will use the matrix multiplication rule to solve this x times beta out, and y is the way it is. Okay, now let's multiply x and beta and see why it must be x and beta. Now, the first thing to check is the dimensions of the two matrices. I mean, here we have a vector beta, but matrix in general. Now, so in order for two matrices to multiply, the number of columns of the first matrix must be the same as the number of rows of the second matrix. Otherwise, you cannot multiply one by the other in this order. No? If you switch the order of the matrix, maybe it's possible. But if they are not the same, then impossible. So that is why here is possible, because we have the number of rows. Sorry, column in X is 3, and number of rows in beta is 3, the same. By that, you can already determine the dimension of the resulting matrix. No? It's actually easy to remember this way now. So after checking, okay, columns equals rows of the other, then you can forget it. And the new matrix will have dimension as the number of rows of the first matrix times the number of columns of the second matrix. So this is the dimension of the resulting matrix, which is now turned to be a column vector, right? 4 times 1. Okay, so we know that already. 4 times 1. Then how to multiply? So the way it works is, for example, I call this resulting matrix is matrix A. No? Then A1, 1, the first element of the first row of the first column of the resulting matrix, you take the first row of the first matrix, now each element multiply the corresponding elements of the first column of the second matrix. Now, so what I mean was 1 times beta 1, x12 times beta 2, and x13 times beta 3. And then you sum them up, these 3 products, to amount to the element 1, 1. So element 1, 1, first row times first column, and we call that like its corresponding elements times each other, we call it the dotted product. Okay, so now I can delete this and actually write the result here. So 1 times beta 1, right, equals beta 1. Sum up with the second element of the first row, x1, 2 times beta 2. Sorry. And then plus similar x1, 3 times beta 3. No? So that is for the first element. We know that now each row has only one element. No? But we have 4 rows. So let's move on with the second rows of the matrix X. No? So again, 1 times beta 1 plus x22 times beta 2 plus x23 times beta 3. And then again, beta 1 for the third row of x plus x32 times beta 2 plus x33 times beta 3, right? And then the last row is again beta 2 times now x4 2 times beta 2 plus x4 3 times beta 3, and you finish now. So each row has only one element, and this element is the sum. No? The sum, the dotted product, so to say. Okay? So now it looks pretty similar to the example that we have. Was that? Yi equals beta 1 plus beta 2x I2 plus beta 3 x I3, right? So now you can answer already 2 questions. Why x beta but not beta x in matrix 1? Because if you write beta x, you wouldn't be able to multiply 3 times 1. No? And imagine here you actually times x after beta, then it's 4 times 3. No? And this, the number of columns of the first matrix and the number of rows of the second matrix does not make much. So that's not possible. That's the first rule. No? So that rule of matrix multiplication you could find on slide 21. Okay. Now only the epsilon missing here and here, right? So what we do, we will sum it with the vector of the arrow term, which is the column vector, and it has 4 row, right? So this is epsilon, and this also have 4 times 1 element. So it's actually easy. The only rule to remember is the dimension must exactly match. So if you have 4 times 1, then the other one must also have 4 times 1. So for this, you can look at slide 15. No. And then we can just sum up the corresponding elements. So the first one with the first one resulting in the first row of the resulting vector. So we have beta 1 plus beta 2 times x12 plus beta 3 times x13 plus epsilon 1. And you do that for each element until the last one. Here we have the fourth one, right? x42 plus beta 3 times x43 plus epsilon 4. Sorry, I lost track. So here should be the plus epsilon 2 and plus epsilon 3. No. And then you will see each of these column vectors already looks exactly what you have in the beginning. No? So this, the dimensions also 4 times 1. No? So the one you want to sum up and the resulting must have the same dimension as the first one. And this result we call system of linear equations. And we have 4 equations for 4 observations, so each equation is for 1 observation. Now, and now you also should know already why, the reason why we have the first column of x is 1s everywhere on the first column. Remember? Usually when you do the regression in the software, then the software will ultimately add this column for you when you choose intercept, yes. However, in some cases, when you have to do the regression manually by yourself, then don't forget to add that.